Very good. Now it's recording. I apologize. So anyway, once the sample has been extruded and trimmed in this miter box, we want to remove the sample from the miter box, and we do this very carefully, not to damage the sample in any way. Okay. And we do that very easily. Luckily, I've prepared. So we'll put that to the side. And now we have our sample ready to go. You can see there is a crease and a cut in this one. Probably not going to test this sample, but I'm using it for demonstration. I'm going to take my calipers and measure the diameter in multiple locations, so I have an accurate representation of what the diameter is. I'm also going to measure the height of the sample and record those. Take those in multiple locations, at least 3, and take an average. Write those down, record those, because the size of the sample is very important to A, making sure you're following the standard, and B, making sure that we understand the unit weight of the soil, the density of the soil as well. I will also take this sample and weigh it on a scale, so I have the weight to calculate the bulk density. So this is our prepared sample. Okay, we want to make sure we don't have it out and exposed to lose too much moisture. Again, we want to make sure this is going to be, we're going to do a consolidated undrained test. So we're going to we want this to be saturated and not dried. The next step then is to prepare the sample. This is the rubber membrane that is utilized. It has a lot of talcum powder on it to make sure that the rubber does not deteriorate. They will over time, especially if they're wet. You want to store these with talcum powder in Ziploc bags is what we typically do. These are new. So we've got this completely open. And what I do then is we have this little cool device that we wrap the membrane over, because we don't want to just put it on there and potentially damage the sample. So we got this cool device. So I've wrapped it around this thing. It has a little hole in it. And what I can do is utilize a vacuum supply, and that vacuum sucks the membrane against the walls of this, so I can easily slip it right over the sample without any kind of damage or issue, center it up, and then I can remove that vacuum, and now it is ready for preparation. And I just remove the rubber membrane out. What we also have too is we have filter paper that we can put on the top and the bottom, and we have porous stones that we can put on top of that. And what that does is we want to separate just the water coming in and out of the sample, but keep the sample secure and all the particles within the membrane. And we can easily go ahead and remove this, and you have the rubber membrane around the sample. Okay. All right, I've already done this part of it for the sample that we have in the machine. So we're going to get over to that. But first, do you have any questions? You have to tell me no if you don't.
Okay. Paul has a question. Hang on just a second. Oh,
what's that?
Okay. Paul said never mind. No questions.
Paul said no? Okay. That's fine. Okay. So we're going to come over to the machine now. Yeah, let's go right about there. I'm going to get a tad closer right about here. Good stuff. Okay. So this is the load frame. Okay. We have vertical beams and a cross beam up top here. Okay. This cross beam has attached to it a load cell. This is an S-type load cell that measures force. Also attached to this is an LVDT, which is a distance or displacement measurement device that does this electronically through cables into that data acquisition unit. You see at the top, that data acquisition unit converts the voltage output from a digital or from an analog to a digital readout. And we can get physical measurements electronically produced into the computer program, which Axel will show you right here. This is the screen that utilizes the computer program. Okay. And as you can see right here, we've got some graphs on here. I think I've shown this to you before. What we're looking at is the change in volume. This is really the amount of water output. And this is, this graph is the pore water pressure that's in the inside of the sample. Okay. And all that is done electronically through these devices here. We've got pressure down here through each one of these that we can monitor the inside pore water pressure, the outside confining stress to the sample itself. This sample is inside here and there's water already around it, okay? And we've been forcing water in. We want to make sure that the sample is saturated, okay? We can't do this test unless we simulate what is going on underneath the ground. So we're saturating the soil sample right now as we speak, actually, okay? All right, so this is pretty complex piece of machinery. As you can see over this side, we have something called a pressure panel. This supplies water and pressurized water to the sample to make sure that we can confine the sample for sigma 3, right? The confining stress to the sample itself. We need to do that with this device right here, this pressure panel, okay? This pressure panel also has vacuum because we want to force water into the sample. But if you remember the specific gravity test we did last semester, what we did was we weighed water after we removed air from it, if y'all recall that. The same concept applies here. If we are forcing water into this to get it saturated again because it has not been saturated because it was removed, but the water has air in it, we're just putting air back into it. So we want this to be de-aired water. So we have a vacuum source that removes the air from the water itself in the pressure panel. Okay. All right, so that being the case, we can go ahead and begin the test. I've already done that. We put the sample in. You can see the membrane on the outside. Okay, you can see there are some O-rings. These are O-rings here that are keeping the membrane tight against the, there's a top platen and a bottom pedestal that it sits on, the sample sits on, and these O-rings go around the membrane to make sure they are sealed. So the outside water does not penetrate into the soil and the water that's in the inside. Okay, we don't want leaks between them. There's tubing inside here, as you can see. That tubing is just from this tube on the outside into the sample, and we've got tubing at the top, and then we also have holes at the bottom. The holes at the bottom are measuring the pore water pressure on the inside. The tubes going to the top are forcing pressurized water inside to get it saturated. Okay. And obviously we have tubes going into the outside of the sample to keep the pressure sigma 3 going as well. We have not started the shearing yet. We're just verifying the consolidation, the C in the CU test, okay? This is a consolidated undrained test, all right? So we're at the point now where we need to make sure we are saturated. So we're gonna go to the computer, okay? Go to the computer screen, and we're gonna take a look at a couple of things. I'm not sure you can see those lines very well, but we have pore water pressure here and we have the volume input there. We're going to go ahead and move on to another test stage. I'm going to check the B value, and the B value is really just saying it's the amount of saturation that the soil sample is experiencing, okay? So we're going to confirm the cell or the confining stress and the pore water pressure right now. I'm just going to follow the instructions. This software is great because it tells you all the instructions. You don't have to go over here. And then we're going to adjust the cell pressure. Let's go ahead and adjust the cell pressure. I'm going to do it myself here. 45. All right, so I'm just adjusting the pressure on the pressure panel. And we have live readings on the screen as well. You can see them right here. And so I can verify that we have that amount of pressure. I'm just, again, following the instructions. And now what's happening here is I am applying increased cell pressure to the sample. Okay, I am applying 5 psi more pressure to the outside of the sample. If this sample is truly saturated, the pore water pressure on the inside will equal the change in pore water pressure, will equal the amount of change and stress that I put on the sigma 3. Remember, we talked about that for consolidation purposes. If I apply instantaneously 2 tons per square foot stress on the soil and the water has not had time to escape, the pore water pressure is exactly 2 tons per square foot to begin with, okay? And that way, you've got to make sure that we would be saturated if the pressure on the inside is the same as the pressure on the outside, the difference in the pressures, right? Because it is related to how much stress we are applying to the outside of the sample and what the inside is. So as you can see from the screen here, I'm not sure you can see these values, but right now, the pore water pressure started at 39 and it's at 43. If you take the change in the confining stress, if you take the change in pore water pressure divided by the change in confining stress, you should be close to about 1. And so right now we are at 0.77. The rule is we need to be at least 0.9 or above to begin the shearing because we want to be saturated close to 90%. And for a soil sample not underground in its environment to be at 90% saturation is very difficult to do in a laboratory, but they allow, or 95, I'm sorry, it's 95%. They want us to be at 95. It's very difficult to do, but we can get close to 100%, okay? So this is not going to be, and we don't have time to wait for it to get to 100%. I'll continue to do that on my own, but we're going to go ahead and we're going to pretend like this is 95.95 or 95% saturated. That way we can go on to preparing it for shearing, okay? So now what I'm going to do is adjust these pressures to make sure that we have a sigma 3 of 20 PSI, which was something I prescribed when I began the test. I decided I want a confining stress of 20 PSI difference, or 20 PSI. So that's what I'm doing right now. Basically what this means is that I am going to, what I've done is we've got pressure that's going to the inside of the sample and pressure on the outside. We need to make that difference between those two pressures 20 PSI, okay? And that's what I'm doing right now. I'm allowing I'm putting extra pressure in. I'm allowing the pore water pressure to dissipate, to stabilize, if you will. And then I'm going to allow consolidation to occur, okay? And so I'm going to do that right now. And what we have here is consolidation is occurring, meaning we are squeezing that sample with 20 PSI worth of pressure and allowing the soil sample to allow water to escape. This graph on the left side here is the amount of water that's being removed from the soil sample due to the squeezing of it. This is the pore water pressure. It is increasing and it will begin to decrease because we have the drainage valve open. So this will allow the pore water pressure to begin to decrease. It's still increasing from when I applied soil sample to it, okay? Now, the interesting thing about this usually takes this might take 30 minutes to an hour, depending on the soil sample. It might take 12 hours, depending. So I'm not going to spend a whole lot of time doing this, but you can see it's beginning to drop off because the water is allowed to escape. This right here, this plot on the left, is essentially a consolidation graph that we would see from the consolidation test that you guys just turned in for homework, okay? This is going to eventually become asymptotic, and we can go ahead and determine what the consolidation properties are from using this test method as well, okay? But notice the pore water pressure is beginning to dip very, very low, and it will do this for quite some time. But again, I don't want to spend too much time looking at this because I want to show you the actual shearing aspect of it, okay? Now, if this were a UU test, unconsolidated, undrained, this portion of the test would not be being performed. All we would do is put the soil sample in here, confine it, and then begin shearing. We would not allow consolidation to occur. That's the difference between the CU and the UU test. We don't consolidate it, what we just did, checking the B values and all that. And then we also don't wait for drainage to happen during this consolidation process. There's no need for that. And so that's essentially what we're going to do today. We're just pretending like we're not doing that. So I'm going to then, now in this test stage, even though I don't want to because it's not done, but we're going to pretend like it's done, and we're going to get to what we call the compression, and that's where we want to go ahead and begin to shear the sample. We want to be pretty close to the sample, so you go ahead over there. And all I'm doing right now is using the consolidation plot to look at the initial trend to try and get information about how quickly we want to consolidate this. Okay, so I'm just working some numbers here to make sure we get the right amount of information. Okay, so now what we want to do is get everything in place here. We still don't have the force transducer in place. So we're going to go that. Move it up a little bit. So what I'm doing is I'm moving the platform here upwards. Okay, no, we don't have it. Just do that. This platform here is moving upwards from this piston here. Good. And then I'm also going to make sure we are monitoring the amount of movement as well. Okay. I'm going to move these down. And what this does is this allows this piston, this platform is going to rise against this piston right here against the load cell, so we can measure the amount of movement we've had. Okay. And that's going to force this piston into the sample, onto the top, and then that is going to push the sample down. And that's our delta sigma in our equation that we add to the sigma 3 to get our final stress. Okay, so we're going to get that prepared right now. We've got those set up. You're good for now. And all I'm doing is zeroing these. And then I'm going to push run, and it's going to begin pushing that piston into the triaxial cell, and then it's going to force the sample to begin to consolidate. We have a while that's doing that, we have some interesting readings on the screen here. So if we go over to the screen, okay, we can see that we have stress versus strain, pore water pressure versus axial strain. So we're monitoring the pore water pressure, but we are getting a stress strain curve as this is in real time, as this is being sheared, okay? And we can go back to the sample here. As it's being sheared, we don't really see any, I don't see any shear planes quite yet. Do you see something over there? Oh, it's starting to bulge, it looks like. Yeah, and starting to crack here. See the edge right there? I don't know if you can see that. This edge cracking right here. And it's bulging too over that edge, but it's beginning to shear right along this plane. Do you see that? I'm not sure you can see that very well. But that looks great. It's really good. So it's shearing, but it's still increasing in, if you look at the plot, the stress strain curve is still increasing, so we haven't hit peak strength yet. Okay. Looks very close. It'll begin to shear and finalize here soon. That's great stuff. That looks good. So you can see the shear plane right here. Pretty interesting. Okay. We have a 25 PSI, what we call corrected deviator stress, or that's the stress, remember, related to the delta sigma added back to the confining stress, or sigma 3, to give us our maximum principal stress. Okay. You can see what we're waiting for here is for these plots to become to peak and then drop down. The pore water pressure will eventually drop, and then we will know what the pore water pressure is at failure, and we will know the deviator stress, and it will calculate then all of our sigma 1, sigma 3, and then be to allow us to plot our Moore's circle. Okay. All right. So to respect the time for everybody, I'm going to stop the shearing and assume that that is the peak. Okay. Now what I'm going to do is go ahead and show you what the results are going to look like. Okay, we want to we'll go ahead and 2.7 for specific gravity. And we'll put in some dummy data in here because I didn't do a moisture content. Let's see. Save that data. And now what we see here is we can go ahead and choose where the failure was, which is just fine. Analysis complete. And then we're going to write a report here. This is just letting the computer do all the things it needs to do. It's filling in a Word document. This is just the software stuff doing some fancy stuff, but basically getting all the information into one document, plotting that for us. This is the saturation aspects. These are all of the details of the sample itself. And eventually what we're going to get to, here's our shearing plots. That's our shear stress. This would be obviously complete charts. This is our Q versus P prime. This is basically a chart that talks about the path of stresses that went through. We can talk about that a little more advanced next semester. These are the conditions at failure. And then you can draw a picture or take a picture and import that in to show where the stress failure occurred. Exactly. But the last piece to this is really important. We want to now we want to group them together, and we see the Moore circle. Hopefully you can see that Moore circle being plotted. And what we can do is, if it's normally consolidated or it's a sand, we can go ahead and adjust this, but typically we would want to have 2 circles, and we would adjust this line to be asymptotic to 2. We only did 1, so we're assuming that there's no there's no cohesion. So we would get a report that looks something like that, where we have 34 degrees for a Mohr circle and no cohesion. Now, obviously, for this sample, that may or may not be true because we didn't do more than one. We would have what we would do is increase the stress and have a nether circle there and be able to have a better asymptotic Mohr circle. But this software does that for us. Okay. All right. So the last thing to do is to remove the soil sample from the chamber and get a final moisture content on that. I kind of made up those numbers. Okay. All right. So that is triaxial testing. It's very complex. It does take a little while to do, but it's not overly complex to where we can't understand it. You've seen one now, and you will see them in the future if you ever go into geotechnical engineering. Okay. All right. So I'm going to come back up now, and y'all get started on your assignment. I'll be up there in just a minute to answer any questions. Okay.